Hello everyone, in the graph part 2 we have seen graph traversal like breadth first search, depth first search, and in that we have seen that a graph can be divided into different components. The connection, the edge in the given graph need not to be, for example, for a given two nodes, that two nodes need not to be necessarily have to be connected with one another. Right, a graph can be a disconnected graph. It doesn't have to have a connection all the time. Right, a graph can be disconnected, but we consider the whole thing as a single graph. We don't consider the graph which are not connected with one another as separate two graphs, but instead we consider that whole diagram, whole structure as a single unit graph, and we say that the graph is divided into different components. And for that components also I have shown you how we perform breadth first search and depth first search for componental graph. Okay, now in this session what we are gonna learn is we're gonna learn first of all cycle, what is a cycle, and different cycle detection algorithms. After it we will talk about what is a bipartite graph, and there is an algorithm called as topological sort and Kahn's algorithm. So we will talk about this four things in this session. So let us talk about what is a cycle. So here if I separate graph based on direction, then we have two different types of graph, right? For example, let us say that I have undirected graph and I have a directed graph. So a cycle, if you recall the concept of linked list, in linked list we have studied a concept called as Floyd cycle detection algorithm. So in linked list, generally a linked list is a linear data structure, and we don't want a linked list to form a cycle in itself. So in order to avoid this looping, in order to avoid this cycle formation, we use an algorithm called as Floyd cycle detection algorithm. And by using this algorithm, first of all we will detect whether the cycle exists or not, and if it is existing, then first of all we will change the direction of at the point of formation of cycle, we will change the direction of that node next value in order to remove the cycle from the linked list, because we know that linked list is a linear data structure, and in trees we don't have any cycles. We haven't seen a condition where a cycle is forming in trees, whether it might be AVL, BST or whatever. In trees we don't have any cycle formation. In linked list, whenever a cycle is formed, we try to remove it because linked list is a linear data structure. But in graph it is very common to have cycles. Whatever the things we have studied in this diagram, you can see that we have cycle formation. So for undirected graph, whenever there is a closed loop, whenever there is a formation of closed loop, then you can say that at that particular point a cycle is formed. And for directed graph, whenever I am reaching a point after traversing, I am reaching again to the same point of my traversal, then I can say that a cycle exists in the directed graph. For example, here I can give you an example. Let us say that for undirected graph I am having a something graph like this: 1, 2, 3, 3 is pointing to 4, 4 is pointing to 5, and I am pointing 1 is pointing to 3. So in this you can see that between 1, 2, 3 there is a loop formation, there is a closed structure. And in undirected graph, whenever we see a closed structure, then it is a indirect implication that there is a cycle in that thing. Okay, are we good? And for directed graph I can give you an example. Let us say that I am having a graph, directed graph, something like this. Okay, so let us consider that this is my source and I am performing my traversal. Whenever I am getting a case in directed graph, if after traversal, if I am coming back to my same node which I have already visited, then it is a cycle condition. There exists a cycle. This is how we will tell whether the cycle exists or not. Here you can see that after traversal I will come back to the same source node after some time. Whenever I encounter a node which is already visited in my cycle directed graph, then it is an indication that there exists a cycle. Okay, now to detect whether a cycle exists or not in a graph for both directed and undirected graph, we use different algorithms, and some of them are, for example, for undirected graph we use 3 different types of algorithm. For example, we use DFS algorithm. What we do is that we will take the same DFS but we will modify it little bit, okay? And the second type is we use BFS. We can use BFS to detect cycle in undirected graph. And the third algorithm we use is union disjoint algorithm. Union disjoint algorithm. Okay, and for directed graph, to detect whether the cycle exists or not, we use depth first search, breadth first search, and there is an algorithm called as topological sort, which is basically Kahn's algorithm, right? Kahn's algorithm. So by using Kahn's algorithm, we can detect whether the cycle exists or not in a directed graph. These are the different algorithms that we use to detect whether the cycle exists or not in both directed and undirected graph. In this session, we will see how we can apply DFS for directed and undirected graph and how we can detect whether the cycle exists or not using DFS algorithm. Now let us talk about cycle detection. So in the first diagram, in an undirected graph, this is the undirected graph, right? So in the first diagram, what I told you, if cycle exists, then you can easily observe whatever the graph you are constructing. In that graph you will see a closed loop, and here you can see that this one is a closed loop and this will become another closed loop. Here two closed structures, closed loops are existing. So if I apply my DFS algorithm, whatever the DFS algorithm which I am creating, if I apply that algorithm, then for this my cycle detection should give me true, because in the given structure there exists a cycle. And for the second diagram, you can see that there is no closed loop. The graph is open-ended, and whenever the graph is open-ended for undirected graph, right, in that case there is no cycle. In that case I will return false. Now let us talk about how we apply our DFS algorithm in the given graph. Okay, in the given graph, how I will apply DFS, and using this DFS, how I can tell whether the cycle exists in my graph or not. So to understand that, first thing you need to understand is that here, whatever the DFS algorithm I have written, I will use the same concept. I will take that code, copy that code, and I will paste it here. But along with the copy and paste method, along with the previous code, I will apply my own logic here, right? First of all, I will observe the diagram, and after observing the diagram, I will extract some logical abstraction, logical conclusions from it, and from this logical conclusions, I will modify my DFS algorithm. I hope you are very clear with me. Okay, so what I will do is that first of all I will observe my graph, and after observing I will extract some logical conclusions, and this, based on this logical conclusions, I will modify my DFS code. Okay, so to observe, for example, let us say that this is the graph I am having and this is my source node, and let us consider that this is not the connection I am having. Actually this is the connection. So my graph is looking something like this. 0, 0 is connected to 1, 1 is connected to 2, like this. The nodes are connected to one another, right? Now this is my source node. Okay, from source node I am applying DFS. DFS says that go to immediate first neighbor, so I will go to 1, and after that I will go to 2. Now I will observe 2. I will observe the second node, and first of all let us observe this. So for a given node, whatever the node might be, for a given node, here I am extracting the logic, I am forming the logic here. That is, for a given node, it can have 3 types of neighbors. It can have 3 types of different neighbors, right? So the first type of neighbor is that the visited of that neighbor can be true, and that particular node can be the current node's parent. right? What I mean by parent is that, for example, here this is my source node, right? From source node I am going to 1, and from 1 I am going to 2. So for this node 2, the parent node is 1, okay? And for 2, for if you observe the node 2, its neighbors, for node 2 the neighbors are 0, 1 and 4. These are the three different neighbors this node 2 is having, okay? So a particular node, a general node, whatever the node might be, it can have three different types of neighbors. The first type of neighbor is that the visited of that neighbor is true and it is a parent. In this case, if I got this case, then I will do nothing, right? I will basically continue my process, my finding cycle process. I will continue whenever I encounter this thing. And the second condition is I haven't visited the neighbor. If I haven't visited the neighbor, then I will perform my DFS and I will visit that node first, okay? If the neighbor is not yet visited, then I will visit that neighbor. And the third type of condition can be visited of neighbor is true. It means that I have visited the neighbor, and along with that it is not a parent. If I am getting this condition, then I will immediately return true. If I am getting any of this condition, then there exists a cycle in my graph. This is my approach, this is my logic here. That is, for example, let us observe this thing. So first of all, I am visiting 0, I am making 0 visiting as 2. After that, I am visiting 1 and I am making visited of 1 as true. Now I am coming to 2. Now let us observe this node 2. So node 2 is having three neighbors, that is 0, 1 and 4. So 0 is a neighbor whose visited is true and it is not a parent. And 1 is a parent, and 4, this 4 node is not yet visited. The visited of this is false. So what I will do, first of all, I will check my first condition. Okay, 1 is my parent node. Okay, if this is the case, then I will do nothing. For this case, I will do nothing, right? I will do nothing here, and I will go to my second condition. Second condition is this, okay, this 4 is not visited. I will visit 4, and after that I will check this third condition. The third condition is for 0. If you observe this node, the visited of this node is true and it is not a parent. If I am getting this condition, then this condition says that immediately return true. So for this, I will immediately return true, and you can see that in the diagram here I am having a cycle. Like this. Here I am having a cycle. So whenever I am getting this condition, this third condition, then I will return true, else I will return false. I hope you are getting it. I hope you got the logic. Now when we code this thing, it will become very easy to understand, right? When we see the code, it will become very clear to you guys. Okay, let us code this thing. So in the program, first of all, I have imported import java.util.star. After that, I have created my normal weight class, and in the create graph function, I am creating this graph. This graph basically I am creating, and all the edge weight is 1. So I am assigning all the edge weight as 1, and basically I am creating this graph. Now what I will do is that, first of all, I will create a function called as boolean type function, because I will return true or false. If cycle exists, then I will return true. If cycle doesn't exist, then I will return false. So static boolean type function, boolean detect cycle. In the detect cycle function, what I will do is that I will pass my graph, array list of edge graph. I will pass my graph, and in this graph, in this what I will do is that, first of all, to keep track whether a node is already visited or not, I will create my boolean type array. So boolean visited is equals to new boolean of graph.length, right? Whatever the nodes length I am having, I am creating it. Now what I will do is that I will run a loop for int I is equals to 0 and I should be less than graph.length and I plus plus in this what I will do is that if my visited is not true, if my particular node is not visited, then I will call my detect util function, and in the util function I will perform all my work, all my actual work. Okay, so if my detect cycle util function is returning me true, then I will return true, and in the util function I will pass my graph, and my visited array and the current node, the node which I am at. And for parent, if you observe, for this source node it don't have any parent. If it doesn't have any parent, then I will pass -1. So here I will pass -1 as my parameter. And if this util function, this is the actual function, this is the real function, in the util I will check whether the cycle exists or not, and this detect cycle will check for all the components. If the graph is divided into different components, then for this different components my detect util function will run a loop for all the components, and it will check for each and every component whether the node cycle exists or not. If it exists, then I will return true, else I will return false. Okay, here I will return true. Okay, else I will return finally false. Now let us define the function. My public static util function, detect cycle util. So I will create this as boolean detect cycle util, and in this I will pass my graph, array list of h graph, comma my visited array, so boolean visited array, my current node int current, and my parent node, right? My parent node. In this what I will do is that first of all I will make the current as true, first of all, because whenever I call for a current node, whenever I call util function, it means that I have visited that node. Okay, so I will first of all make the current as true, visited of current as true. Now for all the edges I will check. So for int I is equals to 0 and I should be less than graph dot length of current dot, here I need to give graph of current dot length, current dot size, and I plus plus. In this first of all I will take the edge, whatever the first edge I am having I will take that. So graph of current dot get ith element, I will get the ith element. Now after getting the ith element I will check different conditions. That is for case 1, that is for the case 1 says that if it is a parent, if the parent is true and visited is true, then do nothing, then it tells that do nothing, so I will not perform anything else. Now the case 2 says that if it is not a parent and the visited of that neighbor is true, then immediately return true. So what I will do is that I will check whether the visited of that e dot destination, that is my neighbor, is true and it is not a parent, that is e dot destination is not equals to my parent node. If this is the case, then I will immediately return true, else what I will do, I will continue my DFS process for the rest of the graph. So else if this is my case 3 will be continue DFS process. So I will continue my DFS process here. Else if my visited is not true, that is I haven't visited my destination node, and the rest of the graph, that is detect util function, is returning me true, then I will return true. That is I will call the same recursive function util, and here I will pass my visited array. Now my current element will become my e dot destination and parent node will become my current node, and if these two are returning me true, then and only I will return true. Else what I will do is that I will come out of this function and I will return finally false. Now in the main program let me remove this. In the main program I will print whatever, first of all I will call my detect cycle function, I will pass my graph, and whatever that function returns me, I am printing it. Now you can see that in the graph, this graph is having a cycle. So if I run this code, then it should return me true. Okay, so let me save this and run. It is showing some kind of error. Okay, okay. So let me save and run this. Yeah, now it will work. You can see that I got the output as true. This is how I will check whether a loop exists in my graph or not, whether a cycle exists in my graph or not. Let me summarize what I am doing. So this function will take care of components. If they are different components, then I will call this detect function. Now this detect function will call detect util function, and in the detect util function I am doing the main work. Okay, so in this what I am doing is that I am passing my graph, I am passing my visited boolean array, my current node, and the parent node of my current node. Okay, whenever I call this function, first of all I am making the visited of current as true. Now after that I am running a loop and I am taking the edges, whatever the neighbors I am having, I am taking that neighbors. After taking that neighbors, what I am doing is I am checking if it is a parent and visited of that parent is true, then do nothing. And the case 2 will be if it is a neighbor whose visited is true and it is not a parent, then it is my second condition, and second condition says that immediately return true. And the third condition is that if the element is not at visited, then call your DFS function and recursively continue your process. So here I am continuing my process. This is what I am doing. Now for this cycle I have shown you for this graph a cycle exists and my output should be true. I have shown you the output. Now let us talk about an interesting concept called as bipartite graph. Let us talk about an interesting concept, and the name of the concept is bipartite graph. We have a graph. Now the meaning of bipartite, bipartite, it is made up of two words, bi and partite. Bi means two and partite means partition, dividing our graph into two independent sets. That thing is known as bipartite graph. So the meaning of bipartite graph is that, for example, I have given you a graph. Now the work of yours is you should divide your graph in such a way that no two adjacent nodes should be in the same set. If you can able to divide that graph into two different pieces, two different sets, such that no two graphs are in same set, then that graph is said to be a bipartite graph, else it is not a bipartite graph. I hope you have understood. And the formal definition of bipartite graph is that a bipartite graph is a graph whose vertices can be divided into two independent sets u and v, such that our vertex u and v, or the direction of graph should be from u to v or v to u, but this u and v, which are two adjacent nodes, should not be in the same set. If they are in the same set, then it is not a bipartite graph. If they are in opposite sets, that is two different independent sets, then it is a bipartite graph. I hope you got the logic here. Now for example, if I want to give you an example, let us consider this as an example. 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, right? And my work is I have a graph. I need to break the graph into two different components, two different sets, such that these two sets should be independent from one another. The elements which are present in the set 1 should not replicate, should not be in the same set, and this division of graph should happen in such a way that the adjacent nodes, that the neighbor nodes should not be in the same set. Okay, so what I will do is that, let us say that I am taking these two nodes. So what I will do, I will add my 0 node in set 1. Let's say I am adding 0 in set 1. Then I should add my 1 node in set 2. Okay, now if I consider this 2, 1 is already present in set 2, then I should add 2 in my set 1. So I will add 2 in my set 1. After that, if I see this, 2 is already present in set 1, then I should add 3 in set 2. So I will add 3 in this. Now in this graph, 0 is present in set 1, 3 is present in set 2. So these two nodes are in opposite sets. Now you can observe that I have divided my graph into two different sets where these two sets are independent from one another. Okay, so if I can able to do that, if I can able to create this partition, then it is said to be a bipartite graph, else it is not a bipartite graph. For example, let us consider that I am having graph something like this: 0 is connected to 1, 2, 3, 4 and 5. Now if I wanna divide this into set 1 and set 2, two different sets, let us say that this is my set 1, set 2. Now if I add 0 in set 1, then I should add 1 and 4, these two nodes in set 2, because for 0 the two adjacent nodes are 1 and 4. So I will add 1 and 4 in set 2. Now if I add 1 in set 2, then I should add 2 in set 1. So I will add 2 and 0 in my set 1. Okay. Now for 4, if 4 is in set 2, then I should add the adjacent nodes which are 0 and 3 in set 1. So I will add 0 is already there in set 1, then I will add 3 in my set 1. Okay. Now here comes the problem. What is the problem? Observe the sets in like clearly. Here you can observe that 2 and 3 are adjacent to one another, and bipartite graph tells me that no two adjacent nodes should be in the same set. But observe the set. Observe the set 1. If you observe the set 1, 2 and 3 which are adjacent to one another, but they are in the same set. If I am getting this condition, it means that there is no way of dividing my graph into two different parts. So this graph is not a bipartite graph. So whatever the algorithm which I am creating to check whether the graph is bipartite or not, for that the algorithm should return me false. I hope you got the logic. I hope you have understood the overall definition of bipartite graph. Now here I am having two diagrams, diagram 1, diagram 2, and I need to check whether the given graphs are bipartite or not. So first of all, pause the video, try it yourself, and after that continue with the lecture. Okay. So first of all, I will check with these two adjacent nodes. I will add 0 in set 1, and if I am adding 0, then 1 should be in set 2. Okay. Now I will check these two. 1 is present in set 2, then I should add 3 in set 1. Now I will check these two. 3 is in set 1, then it means that 2 should be in set 2. Now for this 2, again 0 is present in set 1, 2 is present in set 2. Okay, two different sets. Okay, partitioning is completed. So for this diagram, the output should be true because the given diagram is a bipartite graph. Now let us observe this diagram. This is my set 1 and this is my set 2. Now for this is my source node, and I will add, if I am adding 0 in set 1, then I should add 1 in the opposite set. After it, for this, if 1 is present in set 2, then I should add 3 in my set 1. So I will add 3 here. After it, for this, 3 is in set 1, so add 4 in set 2. Now for this, 4 is present in set 2, so add 2 in set 1. So I will add here. Now for this, I will check 0 and 2. So 0 is added, 2 is also added, but these two are in same set. Two adjacent nodes are in same set, and whenever I reach this condition, I will return false. So this diagram, second diagram, should return me false, and I can't create a bipartite graph for the second diagram. Okay, I hope you have understood. Now let us talk about the approach, how I'm gonna perform whether the given graph is a bipartite or not, how I'm gonna check whether the given graph is a bipartite graph or not. So to do that, we use a concept called as graph coloring. So we will use the concept of graph coloring, and from this graph coloring we can differentiate whether the given graph is a bipartite graph or not. Okay, so what I will do is that I will use BFS algorithm, and along with that I use the concept of graph coloring. Let us understand first of all how graph coloring works. After that I will talk about the code. Okay, so here what I will do is that I will divide my graph into two different colors, because my goal is to divide my graph into two parts, right? So for each and every node I will give some color. Let's say that I am giving yellow and blue color, right? Let us say that I am representing yellow with 0, I am representing blue with 1, and no color. If a node is not having any color, then I am representing it with -1. Okay, I hope you are clear. Now what I will do is that I will initialize whatever the graph might be. The first step will be I will initialize all the nodes in the graph with -1, which is no color. So I will give here -1, -1, -1, -1, -1. Now what I will do is that I will perform my BFS for level wise, right? So this is my level 0, level 1, level 2, right? So for level 0, for my source node I will assign yellow color. So from 0 it will become a yellow color, which is 0. Okay, now I will go to my next level. So whatever the neighbors which are connected to my source node, I will assign the opposite colors to it. So this is my set 1, U set, V set, and U represents yellow color set and V represent blue color set. So I will add 0 in my yellow color. I will add 0 node in my yellow color. Now I will perform breadth first search for its neighbors, and I will assign from no color to opposite color of my source node. I have assigned yellow color to my source node, right? Now I will assign for its neighbor blue color. So I will assign blue color for 1 and 2. It means that I will add 1 and 2 in the blue color set. And for 1, whatever the neighbors are there, you can see that for 1 the neighbors are 0 and 1. So I will add these two nodes in set 1, which is yellow color. So 0 is already present in yellow color, so I will not touch it again. I will check for 3, it is having no color. So from no color I will assign it with yellow color. So I will add 3 in set 1. Now I will come to 3. So for 3, its neighbors color are 1. Okay, its neighbor are 1 and 4. 1's color is blue, but 4 is not assigned with any color. So I will assign for 4th node, for this node I will assign opposite color. Here I am having 0 color, right? So I will assign blue color, that is 1, for my 4th node. So I will add 4 in my set 2, right? Now all the nodes are visited. Now all the nodes in my graph are visited. Now I will check for any nodes, for any adjacent nodes, whether they are having same color. So after BFS and graph coloring, after BFS and graph coloring, my graph looks something like this: 0, 1, 2, okay, this is 3 actually, 3, 4, 2 and 0. Okay, now you can see that 0 is having yellow color, 1 is having blue color, yellow color and blue color. Okay, now I will check whether the two adjacent nodes are having same color or not. You can see that 2 and 4 are having same color blue. If I am reaching this condition, then I will immediately return false in my program. This is what I am gonna do. I hope you have understood the overall approach. Now let us code this thing, and after seeing the code it will become super easy to understand. Okay, so let us code this thing. So first of all I will write my code, and I will make my function Boolean type function, because I am returning whether the given graph is a bipartite or not. If it is a bipartite, then I will return true. If it is not, then I will return false. Okay, so Boolean bipartite. In this I will pass my graph array list of H graph. I will pass my graph. Now after passing graph, what I will do is that first of all I will create a color array. Color is equals to new int of size graph dot length, and all the colors, all the nodes are assigned with -1 color, which is no color. So I will run a loop for int I is equals to 0 and I should be less than graph dot length and I plus plus. In this, what I will do is that I will assign all the nodes with -1. Now after assigning all the nodes with -1, what I will do is that this represents no color. This represents no color. Now I will perform my BFS. Now if you recall the process of BFS, breadth first search, first of all I will create my queue, and after that I will continue my iteration. So first of all I will create my queue of integer type. Integer queue is equals to new linked list. Now after creating queue, I will run a loop for int I is equals to 0 and I should be less than graph dot length and I plus plus. In this, what I will do is that I will check whether the node is -1, whether the color of the node is -1. If it is -1, then it is given that the node is not yet visited. If a node is visited, then I might have colored the node. If I haven't colored the node, it means that I haven't visited the node. So if the color of I is equals to -1, then I will perform my BFS. Here I will start my BFS process. So what I will do is that first of all I will add my source node, which is my ith element. Now after adding my source node, I will assign the color, its color as 0, which is yellow color. I will assign yellow color. Now after assigning yellow color, I will run a loop while for all the neighbors. I need to go for all the neighbors, right? So I will run a loop for queue is not empty. When queue is not empty, I will go into my okay. I will go into my while loop. In the while loop, I will take my current node, that is queue dot remove. After taking the current node, I will run for int j is equals to 0 and j should be less than graph of current dot size and I plus plus, sorry, j plus plus, right? And in this I will iterate, and for all the neighbors node I will assign the opposite color. So here I will check h, I will take h e is equals to graph of curr dot size. Here curr dot size. Now after this, here I need to get the ith element. So get jth element, right? Whatever the element present at that particular level, take that element and check what is the color of that neighbor. So if color of e dot destination is equal, if it is equals to -1, then what I will do is that I will assign opposite color. So what I will do is that I will give next color is equals to color of current, whatever the current it is having. If the color of current node, if let's say I am at my current node, its color is yellow. If it is having yellow color, then its neighbor should have blue color. Let's say I am at my current node and it is having blue color. If it is having blue color, then I should give neighbors yellow color. So if the neighbors is having yellow color, then what I will do is I will give blue color, else I will give yellow color. This is my ternary operator. I am checking if the current node is 0, then I will assign 1. If it is not 0, that is if the current node color is 1, then I will assign 0, right? Okay, now here after calculating the next color, I will assign the next color. So color of e dot destination is equals to my next color. I hope you have understood what I did here. Now after this, I will add my element, I will add that element into my queue. So I will add q dot e dot destination. I will add that node into my queue. Now this is my first condition, and the second condition will be else if I am getting a condition where my color of node and current node color are same. then I will return false. So here color of my destination node is equals to my color of current node. Color of my current node. If this is the case, then I will immediately return false, because this is not a bipartite condition. Here I should give a bracket, and let me remove the bracket here. Okay, this is what my conditions says me. Now if all the conditions are satisfied, then finally I will return true. Like this I will perform my bipartite graph. I hope you have understood the overall approach of bipartite graph, and this code will work for component graph. Whether the graph is divided into components, it doesn't matter, my code will work. Now in the main program, what I'm doing is that in the place of detect cycle, I will call my bipartite function. So bipartite. Okay, and whatever the output it is returning, I am printing it. Now I don't know for this graph whether it is a bipartite or not, so let me save and run this. So you can see that for the given graph, it is not a bipartite graph. I am getting false for this graph. We cannot divide this graph into two different parts. Okay, I hope you have understood the overall approach, code approach for calculating whether the given graph is bipartite or not. Now let us talk about another algorithm. There is a very important algorithm called as topological sort, which is really important in terms of graphs. Whenever you are doing some competitive coding thing, you are expected to find the questions related to topological sort. So a topological sort is basically in graph, it is a sorting technique. You can say that it is a kind of a sort, and it tells you in graph what will come first, what will come second, what will come third. In a linear order, it will tell you which node will come first, which node will come at last. You might not understand it. Let me tell you. For example, the best example is, for example, I want to install Java development kit in my phone. In my computer, I want to install it. So what I will do is that in order to install my Java development kit in my computer, first of all I need to have Chrome or any browser, and I need to have internet connection, and after internet connection I should search for JDK, go to website and install the package in your computer. So the first step is you should have a browser, second step is have internet connection, third step is search for JDK, fourth step is go to the official website, fifth step is install the JDK. So if you observe this is a directed graph in which all the nodes are dependent with one another, and without having the first step you cannot go to the last step, without having the third step you cannot go to the last step. So in order to perform the last step, all these steps should get performed. So this sort of dependency, that is one process, one node is dependent on another node completion. For example, if you want to install JDK, the final step is installation step, but you should have Chrome and all those kind of things. This dependency, this linear dependency, we call this as topological. And if I print the elements in order, for example, if I print this in order, then first of all I need to install my Chrome. After it let me change the pen, this looks very bad here. Okay, so if I print the output in sequence, then I will get the nodes as 1. If 1 happens, then 2, after it 3, after it 4, after it 5, and this order is known as topological sort. And this topological sort is only defined for DAG data structure, which is nothing but a graph in which the graph should be directed and there should be no cycle. A cyclic means no cycle. So the given graph should be a directed graph, and in the given graph in that graph a cycle should not be there, right? For this kind of graph we can define topological sort, right? And topological sort is used only for DAGs, right? We call this DAG as DAGs, which is nothing but directed acyclic graph. So and topological sort is a linear order of vertices such that every directed edge u to v, the vertex u come before v. Here the step 1 comes first, after it step 2 will take place, after it step 3, after it step 4. Like this, in a dependency format, the graph is dependent, the nodes are dependent on other nodes. This sort of data structure we call it as a DAG. DAG is nothing but directed acyclic graph. And if I want to print the sequence of dependence, then that is known as topological sort. I hope you have understood the meaning of topological sort. Now if I want to take a real-time example, then we all know how to make Maggi, right? So the first step will be we boil water. So if I represent the first step as a single node, then the first step will be I need to boil water. Now after boiling water, some people add masala first or some people add Maggi first. So here some people add masala, some people will add masala, and some people will add Maggi, it depending on their choice, taste, all those kind of things, right? But these two things can be done separately and the sequencing doesn't matter. So the stage of these two nodes are same. It means that 2 can take place first or 3 can also take place first. It doesn't matter. If 3 takes place first, then the whole DAG does not get affected. Okay? And if 2 takes place first, then the same, the DAG will not get affected. If the DAG is not getting affected, then the given nodes are said to be in the same state. So 2 and 3 are in same state. Now after it, we will basically serve Maggi, right? We will serve Maggi. At the end, we have to serve the Maggi. Okay, this is the process. Now if I write the topological sort for this, then first of all I need to perform 1. After 1 I can perform 3, after that I can perform 2, and after that I can perform 4. Like this my topological sort will be. Or another output will be 1, after that I will add Maggi, I will add masala, after that I will add Maggi, finally I will serve it. So this can be one type of output, this can be another type of output. So for a topological sort, there might be multiple output, multiple forms of sorting, right? The answers can be in different sequencing. Here you can see that for this example, there are 2 sequences that can be possible. There are 2 topological sequences that can be possible. Either I can add masala first or I can add Maggi first. It doesn't matter, right? So these two, because these two are in same state, so adding this to any of this can go along. But in order to reach 4, in order to serve the Maggi, all these 3 steps should be completed, right? Then and only I can serve my Maggi. I hope you are getting it. So to reach 4, all these 3 steps should be completed. Okay, should get completed. Then and only I can reach my final step. So this is known as a dependency graph. Dependency graph, in which the final node is dependent. In order to go to the final node, we need to traverse all the nodes, all the prior nodes we need to travel, we need to complete. Then and only I can go to the end of that particular graph, right? And whatever the sequencing you are getting in this, you can see that I got the sequence 1 3 2 4 or 1 2 3 4. This sequence is known as topological sort. Okay, now how we gonna do this? How we gonna do this is that we are gonna do topological sort using a modified DFS approach, and another approach will be, there is an algorithm called as very easy algorithm, very easy to understand and easier than modified DFS. Okay, but first of all we will study modified DFS. After it we will study Kahn's algorithm. Okay, so in modified DFS what I will do is that I will perform DFS, and along with that I will create a stack. explicit stack which is I will create in the program, I will give stack of integer. I will create a explicit stack in the program. Now after creating a explicit stack in the program, I will iterate each and every node. For example, let us say that this is my source node and this is my stack. So I will perform my general DFS, but the only change is that I have created a stack in my program. In DFS I didn't create any explicit stack, but here I am creating an explicit stack. Okay, so I am at node 0. Now I will check from 0 where I can go. I cannot go to 4 because the direction is in this way. I cannot go to 5 because the direction is in this way. So from 0 I cannot go nowhere. So I will add 0 into my stack. After that I will go to 1. This is my stack, right? This is my visited array. 0, 1, 2, 3, 4, 5. This is my stack and all the elements are assigned with false. So first of all I am at 0 and I have added 0 into my stack. I will make this as true. Now from 0 I will go to 1 and I will check from where I can go. I am at my node 1 and from 1 where I can go. I cannot go anywhere because there is no direction. So what I will do is that I will add 1 into my stack. I will add 1. After that I will go to the next node. For example, let's say that I am going to this node. So from this node I can go to 1, but 1 is already visited. So I will add 3 into my stack. After that I will go to 2. From 2 I can go to 3, right? But from 2 I cannot go to 5 and 3 is already visited. So if the node is already visited, then I will not go to that node. I will add that node 2 into my stack. So I will add 2 into my stack. After that I will go to node let's say 4. Let's say I'm going to node 4. So at node 4 I can go to 0, I can go to 1, but these two nodes are already visited. So I will add 4 into my stack. Now after that I will go to my final node which is 5, and from 5 I can go to 0 which is already visited. From 5 I can go to 2 which is already visited. So here I will add 5. Now all the elements in my DAG, all the elements are visited. If all the elements are visited, then I will start pop operation in my stack. So if I perform pop operation, if I remove the top elements in my stack, then my output will be 5, 4, 2, 3, 1, 0. And this will become my topological sort. Here what I am doing is that I am adding elements into my stack, based on what comes first. Here 0 is coming first, right? So here you can see that in order to complete 0 I don't need any elements. So I am adding 0 into my stack first, because in order to go to 0 I need to perform 2 elements. Here 5 and 4 should be completed in order to go to 0th element. So I am adding with the element which is having highest dependency, I am adding that element first into my stack. Here you can see that in order to go to step 4, all 3 steps should be completed. And similarly, if you observe the diagram, 0 is the only node which has highest dependency. So I am adding that element into my stack first. After that I am adding next higher dependent element. Like this I am adding, and on top you will observe that the element which I have added has least dependency. So here you can see that 5 has least dependency, 4 has least dependency, but 0 has the most dependency. In order to go to 0, you need to complete all these things. I hope you have understood. So what I will do is that I will perform my general DFS, and in that I will create a stack to keep track of the dependency, and the element which has the highest dependency, I will add that element first into my stack. So when I code this thing, it will become super clear to you guys. So let us talk about the code of this thing. Let me come here. So I will write here public static void top sort. In this I will pass my graph array list of H graph. In this, what I will do is that first of all I will create my boolean visitor type array. Now new boolean of graph dot length. Now what I will do is that I will create a stack here, stack of integer yes is equals to new stack. Now after creating stack, what I will do is that I will run a loop for int I is equals to 0 and I should be less than graph dot length and I plus plus. In this, what I will do is that if the node is not yet visited, that is visited of I is not yet visited, then I will call my top sort util function, top sort util, and this util function will perform my topological sort. So I will pass my graph, my current node, my visited array and my stack. I will pass these things in my graph. Now after performing util, I will come out of my loop and I will perform my while loop and I will start popping whatever the elements present in the stack. I will start popping them. So while stack is not empty, I will write system.out.print. I will remove s.remove the element. Whatever the element present in the stack, I will remove them. Here I need to give pop, not remove. Okay, so pop. Now let us define our util function. So public static void top sort util. Here I will pass my graph array list of h graph and my current node, boolean variable, boolean visited array and my stack. So stack of integer yes. Here I will pass my stack. Now after passing my stack, first of all, whatever the node I am at, I will make the visited of that node as true. So visited of current is equals to true. Here I need to give true. Okay, now after making this as true, what I will do is that I will check for the edges. So int I is equals to 0 and I should be less than graph of current dot size and I plus plus. In this I will check edge E is equals to my graph of current dot get ith element. Whatever the ith immediate element present in my graph, I will take that element. Now after taking that element, if the element is not yet visited, that is visited of the e dot destination, if the destination neighbor element is not yet visited, then I will call my top sort util function for the same thing. But here the current node will become e dot destination and visited stack will remain the same. Now after this, what I will do is that I will add push and I will add my current element. So I will add my current element into my stack. This is what I am doing. Now if you observe that I have told you that top sort will only work for DAG element, which is directed acyclic graph, but in the diagram I have created a undirected graph, so I need to change this thing. So basically I have created a graph something like this. 1 is pointing to 0, 0 is pointing to 2, 2 is pointing to 3 and 3 is pointing to 0. So here I have created a directed acyclic graph, and in the program what I'm gonna do is that I will call my topological sort. Here I will call my topological sort and I will pass my graph. So let me save, and here let me create a graph with vertices v, and here the number of vertices are 0 is pointing to 2, so 0, 1, 2, 3, 4. So here the number of vertices are 4. And I'm calling my create function, and this create function will create a graph something like this, a directed graph. Now what I'm doing is that I'm calling my top sort function. So let me save and run this. So if I run this, then I will get my top sort like this. So for this given graph, where is my graph? for this given graph, my topological sort would be like this. I hope you have understood the overall approach of topological sort. So topological sort using BFS, and which is nothing but Kahn's algorithm. Kahn's algorithm is very simple concept, and it is based on the concept of in degree and out degree. For example, let us consider a node and it is having a node something like this. So for this structure, the in degree of this node is nothing but the number of incoming nodes towards the incoming branches, the incoming edges towards the node. That thing is known as in degree. And for this given diagram, for this given structure, the in degree is 1 and out degree is 2. So what we need to do is that first of all calculate the in degree and the out degree, right? For example, if I take a example of this, for 0, let me write here 0, 1, 2, 3, 4, 5. These are the nodes we are having, right? So for 0, 1, 2, 3, 4, 5. Okay, so for 0 you can observe thus there is no in degree. So here the in degree of 0 will be 0, right? And for 1 there is no in degree. So the in degree of 1 will also become 0. And for 2 the in degree is 1 and the out degree is also 1. So first of all let us talk about in degree, after we will see out degree. So the in degree of 2 is 1, and for 3 the in degree of 3 is also 1, okay? And for 4 the in degree is 0, and for 5 also the in degree is 0. Now let us talk about the out degree. For 0 the out degree is 0, and here sorry. So for 0 the in degree is 2, and for 1 the in degree is also 2, okay? This is a slight mistake here, but yeah. Now if you observe for 0 there is no out degree, there is no edges going out of the node, so the out degree of 0 will become 0. And similarly for 1 also the out degree is 0. Now for 2 there is 1 out degree, so the output will become 1. Similarly for 3 also 1, and for 5 there are 2 out degree nodes, so for 5 the out degree will become 2, and similarly for 4 also there are 2 nodes, 2 edges which are going outwards, so the out degree of this will also become 1. Now you need to understand one thing, that we are talking about dependency, right? And if you recall, let me check here. This is the best example. So in order to install JDK, the first step is you should have Chrome browser or Internet Explorer, Safari, whatever it might be. You should have that in your computer. Now after that you need to install, you need to search in the internet, you need to search JDK, go to their website, install the package. This is the general approach. Now if you observe that for Chrome, in order to have Chrome, what is its dependency, what is its in degree, if you observe this diagram, 1 is 2 is going towards 3, 4 and 5. These are the 5 steps, right? Now my question is, what is the in degree of the first node? The in degree of the first node is 0. So can I say that in a dependency graph, the nodes which are having in degree as 0, those nodes will get printed first. After the second nodes which are having some in degree will like printed next, like this I will go on. So the first node which I should print in this is 1 node, because it is having in degree 0. So the logic here is that in a DAG, in a given DAG, whatever the nodes which is having in degree the least, I will print it at. So here you can see that the in degree of the given nodes is 2, 2, 1, 1, 0, 0, right? So I will print the nodes which is having the least in degree. So the least in degree is 5, after that 4, which is basically 5 and 4 are same. So 4 or 5 or 5 and 4, whatever, the order doesn't matter, but the logic is first of all I will calculate in degree of each and every node in my DAG, and after calculating the in degree, what I will do is that I will print the elements which is having the least in degree first. After it I will print the next element which has somewhat in degree. So first of all I will print 5, 4, after that 3, because 3 and 2 are having same in degree. So 3, 2, after it 1, 0. This will become my topological sort. Right, I hope you got the logic here. Very simple logic. Right, first calculate in degree, and after calculating in degree, print the elements which is having the least in degree and print them in a ascending order. So the element which is having the least in degree will get printed first. The element which is having the most in degree will get printed at last. This is the logic of Kahn's algorithm. And fun fact is that if the given structure is a DAG, then it should have at least one vertex which has at least in degree as 0. Right? Here you can see that the in degree of 5 and 4 is 0. So I will print those elements first. Right? This is the main logic, very simple logic. Now let us code this thing. So the old function which I have created, I am removing that function. Now I will create a new function, public static void top sort, and here I am performing Kahn's algorithm, right? That is why I have removed that, and I will pass my array list of graph, array list of edge here, edge of graph. And in this, what I will do is that first of all I need to calculate in degree. The element which is having the least in degree, I will print that. So first of all, in order to print the in degree, print elements according to the in degree, I should know my in degree elements. So I will create my in degree array. In degree of array is equals to new int of size. Okay. Now what I will do is that basically here you can see that I am using BFS algorithm. So in order to use BFS algorithm, I know that somewhere I am going to use queue. So I will create my queue of integer, q is equals to new linked list. Now after this I will run a loop for int I is equals to 0 here, for int I is equals to 0 and I should be less than graph dot length and I plus plus. In this, what I will do is that if my in degree of I is equals to 0, then I will add that element into my queue. So I will add q dot add, I will add that ith element. Right? Now after this I will perform my BFS, and here before that I will calculate the in degree. So I will write a function cal in degree, and here I will pass my graph. I will pass my graph and in degree array, right? And this cal in degree function will calculate the in degree of each and every index. Now what I am gonna do is that I will perform my actual BFS, that is while q is not empty. While q is not empty, what I will do is that I will calculate int current is equals to q dot remove, general BFS, right? Q dot remove. Now after that I will print the element, whatever the element I am having, I will print the current element. Now after printing the current element, I will calculate the in degree for all the neighbors. So for int j is equals to 0 and j should be less than my graph dot length, graph of current dot size, because I am calculating for neighbors. So dot size and j plus plus. In this, what I will do is that I will calculate edge. Edge e is equals to graph of current dot get jth element. Okay, jth element. Now what I will do is that I will calculate the in degree of my destination, e dot destination minus minus. I will decrement it minus by 1, and if in degree of e dot destination is 0, then I will add that element into my queue. So I will add E dot destination. And finally I will print the next line. Here I will print the next line, or dot print next line, or I don't need to print this also. Now let us write a function for calculating in degree. So here I will write, here I need to give graph dot length, graph dot length. Now let us define my in degree function. So public static void in degree. In this I will pass my graph array list of h graph and my in degree array, int in degree array. Now what I will do is that I will calculate for each and every element, I will calculate their in degree. So for int I is equals to 0 and I should be less than graph dot length and I plus plus. In this what I will do is that int v, I will create a variable v is equals to I, and for this v I will try to calculate its in degree neighbors. So int j is equals to 0 and j should be less than my graph of v dot size and j plus plus. In this I will calculate its edges. H is equals to graph dot get graph of my v, graph of j dot get graph of v dot get jth element. Right now after this what I will do is that I will call my in degree function for the same array. After this what I will do is that in the in degree array, in degree of E dot destination, for that element I will increment its in degree by 1. Like this I will calculate for all the neighbors. Right here I need to give cal in. Okay, now let me save this, and if I run this code then I will get my output, the topological sort, which I have written before. I have shown you that in the previous code I have run the code, right? So the same output I will get for Kahn's algorithm also. So let me save and run this. You can see that I got the output as 0, 1, 2, 3, 4, 5. So this is the for this graph which I have created. So for this graph, this is the topological sort. So up to now we have studied cycle detection algorithm, and in that we have seen how we can detect whether the cycle exists or not using DFS. After that we have studied what is a bipartite graph and topological sort using DFS and Kahn's algorithm. I hope you have understood the overall approach and the codes of all these algorithms. Now in the graph part 4 session we are going to talk about Dijkstra's algorithm, Bell-Manford algorithm and all this kind of things. So with that being said, I will see you in the next one.